Hi, I am Suresh Guttikonda and pleased to present our work did with Jason Rambach at Augmented Vision Group, single frame semantic segmentation using multi-modal spherical images. First, let's take a moment to quickly review and summarize this work. Researchers have become increasingly interested in working with omnidirectional images, often known as 360-degree or panoramic or spherical images as 3D sensing equipment become more inexpensive with useful applications in AR and VR. With a ultra-wider field of view, these images provides more immersive and detailed spatial information from a single frame than standard pinhole camera output. Large image distortions and severe object deformations are the key obstacles when working with these spherical images. The current state-of-art ultra-wide panoramic methods are either restricted to employ RGB-D only or hand-tailored RGB-D depth architectures exclusively. Feeding many complementary data modalities may contribute to a more comprehensive and richer scene interpretation. However, this is still an unexplored area of study. Extensive research on fusion techniques for narrow field of view images have been done in the literature thus far. As these techniques aren't specifically designed for omnidirectional domains or to mitigate distortion artifacts, they frequently exhibit significant accuracy losses when dealing with spherical images. To summarize, dense and comprehensive vision can be obtained by single shot ultra view images. They do, however, exhibit notable visual distortions and panoramic deformations. Moreover, there is a shortage of annotated data in both indoor and outdoor environments. However, an extensive amount of study is available for narrow field of view domain that support a variety of sensor modalities. Nevertheless, they are unable to process ultra-wide perspectives. Through a multi-modal panoramic segmentation architecture, we preserve the advantages of both line of work in our approach and attain a state-of-art performance in indoor panoramic data sets with four distinct complementary type modality combinations. Motivated by recent advances, we devised a transformer-based hierarchical encoder-decoder framework. To keep things simple, let's look at RGB-D depth normals input scenario. Our framework can be used to arbitrary bi-modal and tri-modal input scenarios as well. We go into detail about our framework in the upcoming slides. Building on the work of Zhang et al., we modified the transformer block to overcome the significant distortions in panoramas. Using deformable patch embedding module, distortion-aware features maps are learned to identify the distorted and deformed geometric structures present in the ultra-wide 360-degree images. To do this, deformable convolution operation is used to compute adaptive spatial connection offsets of objects. Comprehensive cross-modal interactions are performed at the end of each encoder stage to reduce the undesired artifacts that are expected to result from noisy measurements and input streams with uncertainties. The cross-modal feature rectification module filters and calibrates each modality's noisy input by using information cues from its complementing sensor modalities. Input feature calibration is done on a local and global level at this step. For every input modality, channel-wise rectification weights are calculated to create corresponding global calibrated feature maps. Subsequently, the computation of spatial-wise rectification weights is done for local calibration. The final rectified feature is obtained by combining the original output with the aforementioned outputs. Information is shared across branches with a cross-attention mechanism prior to combining the rectified feature into a single feature map. To combine the tri-modal features, depth-wide convolution is used in the fusion stage. The resulting feature map is passed through the decoding process to predict semantics. In the decoder step, a lightweight and computationally efficient token mixer is used. Distortion-aware modules are utilized as proposed by Zhang et al. To maintain the adaptivity to object deformations using spatial and channel-wise token mixing. Our cross-modal panoramic model is evaluated using three multi-modal equirectangular semantic segmentation datasets. We provide the threefold validation results for the Stanford 3D 2DS dataset using our methodology in comparison to the existing state-of-the-art methods in this table. By utilizing different modalities for the semantic segmentation task, our approach demonstrates superior performance overall. Additionally, we suppress benchmark results for Matterport 3D and structured 3D datasets in both validation and test splits. In summary, the utilization of textual and geometric disparity information leads in a consistent improvement in performance across the RGBD only baseline situation across datasets. Our approach reliably predicted geometric boundaries with significant better accuracy and object semantics as compared to its peer methods as seen by the visual results displayed on this slide. Additionally, we carried out ablation tests and compared the results using various fusion strategies in our multi-modal panoramic architecture encoder stage. To conclude, we proposed a framework with cross-modal interactions and distortion awareness to a hierarchical multi-modal panoramic encoder design. In three indoor panoramic view datasets, we achieved state-of-the-art performance by leveraging textual disparity and geometric feature cues. Regarding paper and implementation, kindly scan the QR codes if you are interested. Thank you for your time.